Greetings, everyone, and welcome to today's webinar. Before we get started, we want to remind everyone that early rate registration for ION GNSS 2021 ends this Friday, August 20th. ION GNSS will be held in a hybrid virtual and physical environment. Will be taking place September 20th through the 24th in St. Louis, Missouri, and online. Go to ion.org/GNSS for more information. Today's webinar will be presented by Dr. Steve Langle, one of the paper's authors. Dr. Langle received his PhD in Mechanical and Aerospace Engineering from the Illinois Institute of Technology in 2014 and has worked at the MITRE Corporation since 2015, where he's a senior member of the technical staff. We greatly appreciate the time and work that Steve put into today's webinar based on the journal paper in navigation titled Overbounding: The Effect of Uncertain Gauss Markov Noise in Kalman Filtering. That was published in the summer 2021 issue of Navigation, written by Dr. Langle, Omar Garcia Crispillo, and Matthew Yorger. We'll put a link to the full paper that you can download free of charge on our website. Following the presentation, Dr. Langle will accept questions. You can use the Q&A button to ask a question. We'll address those at the end. And a recording of today's presentation will also be available via our website within 24 hours. With that, we thank you for being here, and we now turn the time over to Steve.
Okay, thanks very much, Rick. Let me hopefully, Rick, can you confirm you can see everything? Okay.
Yep, looks good.
Okay, great. So thanks very much for the introduction. So first of all, on behalf of myself and my co-authors, we're excited to be able to participate in this and share some of the interesting work we've done that follows on some existing work in the literature. It's a dense read, so I'll warn you in advance. I tried to keep the technical details somewhat to a minimum, but they're sprinkled throughout. So feel free to ask questions as they come up. We have a bit of a packed talk today. I'll do my best to keep it down to around 40 minutes to save time for questions and discussion. But just a quick outline here, what I want to cover. So first and foremost, this paper pertains to sequential filtering. That may not be obvious to everyone. Why am I considering that particular approach? So I want to discuss a little bit motivation for sequential filtering, what it means to robustly model correlated noise. That can be a little bit tricky depending on what you want to do with those models. And then I want to cover a new result for uncertain Gauss Markov processes that was published back in 2009. Highlight the proof of that result and some extensions beyond what was already in the existing literature. We'll look at the implications and demonstration for an illustrative, simple 1D example. And then we'll talk about a real-life example, which is application to sequential ARAIN for LPV 200 navigation. And then we'll conclude here with some concluding remarks and lots of interesting follow-on work that's happening right now. So some quick background and motivation here. It goes without saying that the number of applications requiring navigation has exploded in recent years. Pretty much every application you can think of requires some kind of navigation. Snapshot least squares estimation, especially with GNSS, continues to be sufficient for many of these applications. Particularly if you're talking about open sky navigation in a clean environment. Clean just meaning there's no deliberate interference or interfering signals. That's one instance. Or aircraft navigation using multi-GNSS. That's another open sky application. You can pretty much get away with just taking a snapshot of pseudo range measurements, pumping it into a least squares estimator, and getting a position solution. Given that the proliferation of navigation to other applications, sequential estimation is starting to become more common and in fact necessary. One of the more obvious instances where you might want to consider a sequential approach is where you don't have an open sky environment, instances of sky blockage. So here's an example, autonomous refueling. That the refueling tanker introduces a lot of sky blockage to the refueling aircraft. A more common example for most of us might be urban canyon navigation, driving in a city, these kinds of things. There's also instances of denial of GPS where I don't have GPS at all. So how am I going to navigate if I don't have GNSS signals? Well, maybe I need to include an IMU or some other kind of sensor to provide continuity. So those are instances where you need maybe a sequential estimation approach to bridge outages or provide continuity of service. Another one is not necessarily that I don't have access to signals. I could still have clear sky environment. But accuracy and integrity requirements are getting tighter and tighter. Aircraft vertical guidance with depleted constellations, for example, is one application where, yes, I have more than enough signals to do a snapshot solution, but I can't meet my accuracy requirements. I need to have the averaging benefit of sequential filtering. Autonomous vehicles, a similar application where you have very, very stringent accuracy and integrity requirements, just can't be achieved with the snapshot approach. So needless to say, sequential filtering is becoming more and more common. We see it all over the place, and I suspect it's going to probably become more of the norm than the exception going forward. So we could have a whole webinar exclusively devoted to sequential estimation. There are numerous methods: Kalman filters, unscented filters, particle filters, all kinds of stuff. But for us, I think it's safe to say that the Kalman filter still remains probably the most widely used. Certainly the one that people probably gravitate to first before maybe considering something more elaborate like a particle filter. But for that reason, this paper, our paper, focuses exclusively on Kalman filters. So one of the key challenges here is how do you develop robust models for process and measurement noise? So one of the things that we have to deal with sequential filtering that we don't have to do with snapshot least squares estimation, for example, you've got to capture behavior over time. So GPS measurement errors, if you're thinking about GNSS or GPS in particular, measurement errors tend to exhibit time correlation. So in the bottom right corner here is an example of what I mean by that. Here's an example of pseudo-range multipath error on a particular satellite that came from a reference that I have here. And if you look at that, if you look at the way that multipath error behaves, it's not just random from one time instant to the next. There's an obvious structure, sinusoidal in this case. So not white noise, correlated. We have to tell the filter that structure exists. So there are lots of methods to develop models, but the simple fact is, models are never exact. They're models, that's why they're called models. And they can, if you're not careful, they can produce misleading predictions of estimate error distributions for the Kalman filter. And that can have, negative consequences downstream if you're using that as a guide to make, certain decisions, like land an aircraft, for instance. So you've got to be, there's care that needs to be exercised when developing these models. So the question is, how do you define them? So application dependent, there's many criteria you might think of, to specify models. One criteria that we're particularly interested here in our paper is, ideally what we'd like to do is specify models so that when the Kalman filter puts out a estimate error covariance matrix, it's larger. When I say larger, I mean in a positive definite sense than what the actual covariance matrix is. That way, it ensures that the covariance matrix overbounds the estimate error distribution. So I'm going to give you a visual interpretation of what this larger in a positive semi-definite sense means in a few slides. But at this point, what I'll say is what it means is the estimate error variance for any state that you care about, you're going to predict a larger variance than what it actually is. That's why I say it's an overbound on the error distribution. So that sounds like a good criteria to use, but what's difficult is if you start to try to develop a mathematical approach for, how can I enforce that criteria when specifying models? The difficulty here is we don't actually know what the underlying correlation structure is. we have no idea what the mathematical structure looks like. On the previous slide, I showed you like a sinusoidal trace. What is it exactly? I don't really know. Maybe I have bounds, I can bound the autocorrelation function. So in the bottom right corner here, this might be a more reasonable state of knowledge that I might be in for autocorrelation functions. Here, the authors in reference 2 here were concerned about variations in residual troposphere correlation due to differences in relative humidity and wind speed. So they went out, collected data, and empirically estimated autocorrelation functions and got something that looks like this. So I don't know exactly what any one of these is, in a mathematical sense, but maybe I can bound it. So, to dig down a little bit deeper in the criteria, you may suggest, I want to specify models so that sigma is larger than P for any true autocorrelation function living in this region. That might be a more specific criteria. And there's been quite a bit of work, on that type of problem statement. Some of those results are presented in reference 3 here, but I'll cut to the chase that the solutions are not very practical. They are essentially batch type solutions that require you to store the effect of the entire previous history of measurement and process noise on the current time estimate error distribution. So yes, on paper, I can do that. Practically, it doesn't work very well. So there was a pretty interesting result published, even prior to the result I showed on the previous slide back in 2009 that changed the previous problem structure of bounded autocorrelation functions, but took it a little bit further and said, well, let's assume that I also know that there are Gauss Markov processes. So the underlying correlation has a Gauss Markov structure, but I don't necessarily know what the time constant is. So the bottom left figure here is very similar to what I showed on the previous slide, but in this case, I'm enforcing the fact that the autocorrelation functions are exponential. So same kind of interpretation, the true autocorrelation function lives somewhere in between these red bounds, but I'm also enforcing the fact that it has an exponential structure. And so what the authors in reference 4 showed is that if you're in this position where you have a time constant that's unknown but bounded, for a continuous time Kalman filter, if you use this particular model that I boxed here for Gauss Markov noise, then it satisfies the criteria I laid out in the previous slide, which is this will guarantee that sigma is greater than P for any time constant in the admissible range. And it's a pretty powerful result, really. It's quite simple, actually. That it's if you start thinking about it a little bit, kind of makes some sense. But until we came across this paper, it was a result that wasn't really largely known to the navigation community. And again, when I say sigma greater than P, I just want to make it clear what that really means. It just means that the estimate error variance predicted by the filter is going to overbound. It's going to be larger than what the actual variance is, regardless of the state I care about. I could have a multi-state filter. I might be interested in position or velocity or some combination of those. You're always guaranteed to predict a larger variance than the actual value, which is quite powerful. So what I'll say about reference 4, when I came across it in a separate literature review that I was doing, it was one of those. I think it's one of those instances where you may not necessarily know what you're looking at unless you know what to look for. So it was a tough paper to follow. There's a lot of steps in the proof. I was able to follow it mostly because I've had a history, with this particular problem, but I could understand people that might be coming in from the outside might not quite know what they're actually looking at. In addition, there were a couple of gaps in model initialization. How do you initialize the Gauss Markov model? We have a differential equation for it, but what's the initial condition or requirements on the initial condition? And also there's an open question of how it applies to discrete time Kalman filters. So if you look at reference 4, all of the derivation was done in continuous time. You may be able to make some qualitative arguments that, yeah, it probably should work in discrete time as well, but does it? And so those are, the main goals of our paper. One is to provide a little bit more context and explanatory steps to make the proof more accessible, maybe to this particular audience. A second goal was to settle the initialization and discrete time questions. And third, just to explore implications. What does this mean? In terms of, sigma greater than P, what does that actually mean in terms of a covariance matrix? And, what about an actual application? Is this just really super conservative to the point where, yeah, I have a bound, but it's not really useful? What are we dealing with? So that's why we want to, explore what happens here for a 1D estimation problem and an array application. So I want to give a little bit of highlights of the proof. So if you look at the paper, if you look at our paper in the summer edition, it is quite mathematical. So I'll forewarn you, before you dive into there. But I think it is instructive to highlight, what the approach was that was taken, because it's a different view, I would say, than how we've typically thought about this problem in the past. So the first thing you have to do to make headway on this problem, and it's one of these instances where you may not necessarily know what you're dealing with until you start putting the pieces together on paper. So the first thing you have to realize is that the Kalman filter covariance matrix that's put out by the filter is not the actual covariance matrix if you have this type of model uncertainty. It's a prediction, and our hope is that the prediction is conservative. But if you want to prove conservatism or prove that it's bounding, you've got to first figure out, well, what is the actual covariance given that I have this model uncertainty? So that's the first step here. So the next couple slides, because all of the uncertainty lives in the time update of the Kalman filter, I'm going to focus on that. But of course, in the paper, what the implications are going through a measurement update, those are all covered. I just don't have enough time to cover it here. So you can see find those details in the paper. So the way that this works is, we'll presume up front that the way we're accounting for these, correlated noises through state augmentation, it's a common technique in Kalman filtering to account for correlated noise. So we have some, dynamic model for our augmented state, which I'm calling X here. So X evolves according to some linear dynamic model, Fx plus Q. Q is the process noise here. And then the filter, the Kalman filter is propagating that estimate, but it's not using F, it's using some other matrix F hat. So F hat is different here because I'm using some model for the Gauss Markov noise that might not actually match what it actually is. It's reflecting the fact that I'm using some time constant and process noise covariance that I don't know. So the question that we want to answer here is, can I be smart about how I specify F hat that satisfies this bounding criteria on the covariance matrix? So in the paper, if you look at what the estimate error looks like, so how does the estimate error behave, given the fact that I'm using some transition matrix that doesn't match the truth? It turns out that the estimate error is correlated with the actual Gauss Markov states, which I'll call A. Here, they're intricately tied together. So when you go to propagate or look at what the true covariance matrix is, you can't just look at epsilon in isolation. You've got to keep these two things together. So you've got to look at a larger matrix that is also simultaneously propagating the correlation between the Kalman filter estimate error and the actual Gauss Markov states. So that's, step number one here is to define what that propagation looks like for this matrix P. So P being the true covariance matrix here. And so in the paper, we show that it has this type of structure here. And so now you can explicitly see that there's a delta F involved, delta F being the F minus F hat. If I had no uncertainty, that would just be 0. And of course, there'd be no reason for me to do this kind of, second augmentation step, if you will, because there's no connection at all. So I would just have an ordinary Kalman filter propagation. Now, so the takeaway from this slide is I only care about, the upper left block here, PX, but I need this cross correlation here to account for the fact that the transition matrix is unknown. So you might be thinking, okay, well, if I have an expression, so if that's what the actual covariance matrix is, then why don't I just propagate that? Why am I trying to propagate this other thing that doesn't match? And now I'm going to try and bound it. And that sounds complicated. Why don't I just propagate what the actual matrix is? Well, I would if I could, but the fact is I cannot, because we have this unknown matrix delta F floating around. The approach laid out in reference 4 that we follow in the paper here is we say, all right, I can't propagate P. Let me define a structure for another matrix that I'll call sigma here. But I'm going to be smart about how I define the conditions on this matrix sigma, such that it's going to allow me to actually propagate it without needing to know delta F. And so the key step that was taken in the proof in 4 was to say, I'm going to specify a structure for sigma that basically has the exact same structure as P, that'll allow me to make easy comparisons between the two. I can look at sigma minus P and everything works out nicely. Might not be clear from here, but I hope it's clear from the paper. And the idea is to extract the part that I care about, in this case, the upper left block. That's the only part I really care about here. And when you look at that upper left piece and you take a look at the components that are involved here, I see pieces of stuff that I know. F hat is involved in this expression here. Delta F is there again. So the idea here is to say, all right, since I don't know delta F, I can actually get rid of it by forcing this cross correlation between estimate error and Gauss Markov states to be 0. That's an indirect way for me to eliminate the influence of delta F on the covariance matrix. And that's exactly what we do here. We force that sigma XA to be 0. And then what that does is it sets up constraints with my criteria that I want sigma to be greater than P that ultimately yield the continuous time model presented in reference 4 and that we show in our paper. There's a lot of steps in between, setting up the constraints, interpreting what they mean, how they impact F hat, what does it mean for the process noise. So there's a lot of detail there that I'm not going to be able to cover here, but that hopefully you can follow along in the paper. But that's the gist of how you arrive at this continuous time result. The interesting thing when you start peeling back what the implications of these constraints are, that was not covered in reference 4, that's new in this paper here, is there's an additional constraint by forcing that cross correlation to 0 has implications on how you initialize the variance of the Gauss Markov model. So what we show in our paper is that this additional constraint places limits on how you initialize the variance. And so what we show is that the initial variance of the model has to satisfy the inequality shown here in the middle of the slide. So as long as I initialize the variance of the model with this lower bound or something larger, then I now have a complete specification to guarantee that the Kalman filter covariance matrix will overbound the estimate error distribution. So the boxed result here, before I showed you just the A dot equation, this bottom part here is a missing piece that specifies the initial variance of the model. And what's interesting about this is the model actually turns out to be a non-stationary model. Now, I have freedom to specify however I want to pick that initial variance. I could actually make it larger. If I make it bigger, make it sigma squared times the ratio of the time constant limits, I can make the model stationary, which might be a little bit more intuitive because I know that Gauss Markov processes are stationary. So it makes sense that I use a stationary model. So in that sense, it's more intuitive, but you pay a little bit of a penalty because you've inflated the variance now. So the model tends to be, is more conservative in that case. So, if you want to appeal to intuition, you could make it, make the model conservative, but there's, in terms of, is there any kind of advantage to doing that? Not really. You don't gain any kind of computational advantage by inflating the variance. So what we did for the rest of the paper was focus on the model that's specified here in the bottom left. So as an intermediate summary, the main theoretical contribution, or at least one of the main theoretical contributions of the paper, was to have a complete specification of 2 models for uncertain Gauss Markov noise, a stationary and a non-stationary model, such that when they're used in a state augmented Kalman filter, they guarantee that sigma is larger than P. As I said at the outset, the result was pretty mathematical to go through and establish a guaranteed bound. It does make you wonder, is there something more physical, sort of underpinning what's really going on here? Is there some kind of physical interpretation of what this bound means, of what this model means? And if you start sort of playing around with that, you find some interesting observations. One being that for this particular case, the autocorrelation function of these models actually overbound the actual autocorrelation function for any time constant in the admissible range. So that it might seem like an aha moment. Oh, maybe that means that what's really going on here is I'm overbounding the autocorrelation function. So is that a general result? The answer, unfortunately, is no. That doesn't hold in general. It happens to work out in this case that it does happen to overbound. But there's an illustrative example in section 3 of our paper that shows if you rely on that interpretation alone, you will find that sigma does not always exceed p in that case. So it's not quite overbound the autocorrelation function, but there actually is a broader physical interpretation that I'm going to discuss in the concluding slides here. That goes beyond this Gauss Markov structure. We'll save that for the end. So the last piece here in terms of theoretical contributions for the paper, and this one was actually quite tricky. All of the development in reference 4, everything was done in continuous time. The initial part of our paper focused on a sample data system where I still had continuous time dynamics with discrete time measurements. Now we're going to take it one step further and say, well, most Kalman filters, even if I have a continuous time dynamic model, I discretize that thing anyway. I implement the entire algorithm in discrete time. So what are the implications of proving a result in this sort of mixed mode with a mix of continuous and discrete dynamics carrying over to an entirely discrete system? There are qualitative arguments that you could make, that, okay, it probably should be true that a discrete time version of this bounding model probably overbounds the covariance matrix in discrete time, but actually showing that analytically on paper turns out to be quite difficult. And to give you a hint of like what's the problem, why is it so hard? If you look at the continuous time Kalman filter, it turns out that covariance propagation has this nice Riccati structure where everything's linear in delta F. A delta F matrix comes into that linearly. In discrete time, you wind up having, it's a quadratic structure. You wind up having a delta F term that shows up in a quadratic form. And so that's a term that, am I bounding that term or not is really what this problem comes down to. And for those of you that are interested or ambitious, I would guide you to read Appendix D in our paper, which shows analytically that it is in fact true that if I just take this continuous time model for uncertain Gauss Markov noise, discretize it, you use that in a discrete time Kalman filter, you're still safe in the sense that you have an overbounding covariance matrix. And so that's what the boxed equation is here. All that the boxed equation is on the bottom here is the discrete time equivalent of the continuous time model I showed you on a couple slides ago. So that's the discrete time model here. So before we start talking about results, what I want to highlight is I think the real power of the results from this work is the simplicity of the model. So this is a model that can be implemented very easily in a state augmented Kalman filter. I don't have to do anything special with regards to covariance propagation. I talked a lot in the previous slides about sigma not really being the covariance. There's this other one that's called P. All that stuff was there for the purpose of developing the proof, but it's business as usual. This is the model that I should use for uncertain Gauss Markov noise. And you can see all the key players are in here. I have tau min and tau max. You would expect to see that. This just gets incorporated like any other state augmentation model. So it's I think the real power here is the simplicity with which you can use this result. So I just want to make that clear. don't get too bogged down in all the mathematical details that are underpinning all of it. That's important too, but I really don't want you to forget, the takeaway here that this is easy to implement in a Kalman filter. All right, so enough of the math. I think I beat you enough with that. So let's take a look at some examples here. So the first one I want to look at is just a simple example to get our feet wet about what does this actually mean. So here's a simple 1D estimation problem. I want to estimate the initial position of a vehicle and its constant speed u using noisy measurements of the position. So the measurement errors in this case, it's a sum of white Gaussian noise and a first order Gauss Markov process. True to the assumptions of the paper, we assume that the time constant is unknown. It's somewhere between 10 and 100 seconds. Clairvoyantly, we know that the actual one is 50 seconds, but of course we don't tell the filter that. Filter just knows there's this interval. So we want to estimate initial position, P0 and speed U, and see what we get in terms of a predicted covariance matrix. So if we run over an elapsed time of 200 seconds, so here I'm showing you standard deviation over time using both the stationary and non-stationary models. So if we focus here, for instance, on the non-stationary model, the ones with the black, with the circle markers. So one thing that we would hope to see is that the predicted variance is larger than the actual variance for all time. That's exactly what we see here. The black line is above the gray line, which indicates that we are conservatively estimating or predicting the estimate error standard deviation. Same is true for the stationary model, the solid lines here. But what's interesting is it's this non-stationary model in this case produces noticeably better. So the variance bound using a non-stationary model is significantly lower compared to using a stationary model. So this would be, a no-brainer that in this case, of course, I'd want to use a non-stationary model. If we look at the second state for this example, the speed state, so same plot as before, standard deviation versus time. Again, we see this. This is a little bit hard to see because the lines, your eye almost wants to compare, solid black to black with markers. But again, try to keep your eye looking at the markers. Black markers compared to gray markers, black solid compared to gray solid. Same story as before. I'm predicting an upper bound on the variance. But what's interesting in this case is there really is not much benefit to using a non-stationary model. The black curve with markers is pretty much identical to the black curve that has no markers. So I'm not really getting much benefit in terms of getting a smaller variance bound in this case. So in this particular case, if you happen to want to use a stationary model, you could. You wouldn't really take much of a performance hit if you were interested in this case in the speed state. So probably not too surprising. The benefit of the non-stationary model depends on the state of interest. Could be good for some, maybe not so apparent for others. But again, we got a guaranteed bound in this case. So that was just looking at individual states. Maybe I have an application where I'm interested in a mix of the position and speed state. So remember that the whole point of this was we were supposed to be satisfying the criteria that the covariance matrix is everywhere larger than P, which means that if I was interested in some linear combination of P0 and U, well, then I should still overbound the estimate error variance in that case. So for 2D, in 2 dimensions, visually, what that means is if I was to plot a covariance ellipse using the Kalman filters covariance matrix, that should circumscribe the actual covariance ellipse if I happen to know what the true time constant was. And that's exactly what I'm showing you here on the right-hand plot. So this is the covariance ellipse now for the initial position and speed states predicted by the Kalman filter, which is the black ellipses here. And we're also showing you here what the true covariance ellipses are, given that I know if I knew that the true time constant was 50 seconds. And so we can, in fact, see that the predicted covariance ellipse in black everywhere circumscribes the true covariance ellipse, which means regardless of the state I'm interested in, I'll have an upper bound, predicted by the Kalman filter covariance matrix. So this just, this is reinforcing that it looks like all the math checks out. we're seeing what we expect to see for this simple example. Even if I didn't know the Gauss Markov process time constants, I'm still able to overbound, using a state augmented Kalman filter with a particular model for the Gauss Markov noise. And so that this just should give you a warm fuzzy that, yes, this looks to be behaving correctly. So now to the other question. So we have a demonstration, that's great. Looks like this works well. What does this actually mean for a program of record, if you will? That was to actually implement this for a real system with real requirements for accuracy and integrity. Am I going to predict that I can never use the system because the bound is so loose, or does it work not so bad? And so what we wanted to do in this paper is use an example application in advanced receiver autonomous integrity monitoring. So ARAIM is a system being developed to provide worldwide guidance, autonomous guidance of aircraft. So the baseline ARAIM implementation is a snapshot implementation that uses dual frequency GPS Galileo measurements at one instant of time to achieve LPV 200 navigation. So one of the more interesting cases for ARAIM that's been particularly challenging is LPV 200, but with depleted constellations. So when I have one GPS satellite out and one Galileo satellite out. And what studies have shown is with the baseline implementation is that LPV 200 in that case can only be sparsely achieved. And so you're sort of at the limits of what you can do with a snapshot implementation. Now that being said, studies have shown that with sequential ARAIM, sequential techniques provide better availability for this case of depleted constellations. But it's always been at the back of our minds that, all right, all that availability analysis that I've done still hinges on this, me knowing or somehow knowing how to bound the uncertainty in the time correlation. So all those studies were done, using heuristic approximations that we now know turn out not to be true. But the results of this work now allow us to, fill that void and say, no, now I actually know how to account for that time correlation uncertainty. Let's revisit the availability analysis and see what we get. And so, right, so I think I already covered that on the last bullet here. So the results of this paper allow for realistic assessments of sequential ARAIM availability. And what's exciting is the results show that even though I don't know the exact correlation structure or what the time constants are in this case, sequential ARAIM still significantly outperforms snapshot ARAIM. That's the key takeaway here, which is exciting. So to show you, visually what that looks like, I don't have time to go through all the details of the sequential ARAIM implementation we used here. Suffice it to say, it's an implementation that uses a bank of Kalman filters with multiple hypothesis solution separation. So there's 3 contributions that we're interested in to the correlated noise: raw code and carrier phase multipath and residual troposphere. So I have here in the slide, all the variances are assumed to be known, but we have uncertainty in the time constants with the ranges shown here. For some of the ARAIM people that might be online, that might be curious, well, what about residual satellite clock in orbit? Those are accounted for using a special model in ARAIM, a bias plus ramp model. So we kept that for now in this analysis. That might be something we come back and revisit later, but it's not in this particular example here. So just to give you a demonstration for how well does sequential ARAIM perform at a particular location on the globe compared to snapshot ARAIM. So here we focus on a particular location in Blacksburg, Virginia. And what I'm showing you here is integrity risk versus time. But what I did, what we did is we deliberately reduced the vertical alert limit to 10 meters. And the reason we did that is because this is strictly for visual purposes to show you, to highlight what the benefit is of using sequential versus snapshot. And so what you can see here with the thin line with diamond markers, that's the snapshot implementation. And you can see that that's significantly above the sequential, solid, thick black line here, which is for sequential ARAIM. So the integrity risk is, quite a bit larger for snapshot versus sequential. And this is, again, this is even though, I don't know what the time constants are. We factored all that in, and even though I have that uncertainty, I'm still doing much better with sequential ARAM at this particular location. So if you carry that over and run that analysis at every at grid points around the globe, we get an availability map to compare between snapshot and sequential ARAM. So when we did our availability studies, I want to give you at least some indication of what was actually run here. So on the previous slide, we used the 10-meter val strictly for demonstrative purposes. For the availability analysis, the global availability analysis, we focused on a val, or we used a val of 35 meters, which is more consistent with the requirements. We used we were interested here with LPV 200 with depleted GPS and Galileo. There are additional assumptions that are provided in the paper. So we found for snapshot ARAM, if we look at coverage of 99.5% availability, we find that we only get about 85% coverage using snapshot ARAM, whereas we achieve nearly 98% using sequential ARAM. So roughly a 13% increase in ARAM availability, which is quite significant. So the conclusions, the paper developed robust models for uncertain Gauss Markov noise that can be used in discrete time Kalman filters. The models guarantee that the predicted covariance matrix will overbound the true covariance matrix, even when the Gauss Markov time constants are uncertain or unknown but bounded. The key here is it provides a proven bound. So no more reliance on, it looks like this heuristically makes sense, I should have larger correlation, all this and that. There's a rigorous proof here now that we're safe, at least for the case of Gauss Markov noise. And that last one is a key because that's sort of setting the stage for where we're going. So the result is a big step forward, but it does apply exclusively to noise that's truly first order Gauss Markov that we model as such. We demonstrated the theory for a 1D estimation problem and showed what the implications are for an actual application, which is sequential ARAM with LPV 200 and depleted constellations. So follow-on work, after publication of this work, there's a lot of work that's going on right now that's building on this particular result. So I said before that it looked like overbounding the autocorrelation function might be a more general criteria. We said no, that's not true. But what actually does turn out to be true, that's very fascinating, is that the models, what's really going on here physically, and you can show this, is that the models are overbounding the power spectral density over all frequencies. So we went through a mathematical approach to develop a proven bound, but if you go back to first principles and look at it in a little bit slightly different way, you'll see that what's really going on here is we're specifying models that overbound the power spectral density function. So what does that proof look like? How do you arrive at such a result? There are 3 references here that I point you to on that. And what's really interesting about that is that result applies for all stationary correlated processes, not just Gauss Markov processes, which is critical from a practical perspective because we're never really going to know, a priori that the noise actually is exactly Gauss Markov. So there's a lot of excitement about that. However, what I will say is this result in connection with what we've discovered here for Gauss Markov processes, I do see that could be relevant down the line with regards to non-stationary correlated noise modeling. So that's much further down the road. I don't think we're quite there yet. There's a lot of work to be done on how this all plays out with actual data. So, there was an implicit assumption that we had some knowledge about the true underlying correlation function. But in reality, what am I going to have? I'm going to have estimates of it. So where does that piece fit into all this? The fact that I don't know what the actual autocorrelation function is, but I have estimates of them. That there's much work to be done there. Some progress has been made. I point you to these references here. And even further down the road is, what about non-Gaussian noise, correlated non-Gaussian noise? That sounds like a really hard problem. Jason Reif and Demos Geber Xavier had a very interesting paper in 2007 that looked at this problem, and this idea of PSD overbounding, or the results shown here, have implications for that symmetric overbounding approach that's presented in their work. So we did have a conference paper on that last year. And so I'll point you there for those of you that are interested in, sort of the end goal of all this work, which is to get to, overbounding correlated non-Gaussian noise. So with that, I think I finished pretty much a little bit over my stated goal of 40 minutes, but thank you very much for your attention. I'm happy to take any questions here. So let's see here.
Thanks. Yeah, it looks like we have a couple of questions from the audience. The first question is, ARAIM or RAIM tries to address a systemic fault downstream from the source at ground or in the receiver. This extends the TTA to 6 seconds and provides Cat1. The need is for Cat2 or 3. On the other hand, direct methods for signal integrity have been demonstrated. If you have a comment, I guess there wasn't more of a comment than a question.
Yeah, maybe what the attendee might be getting at is, when I see direct methods for signal integrity, I wonder if they might be referring to, I'm speculating here, but maybe that for certain category approaches, using a snapshot implementation, it's been demonstrated that there's sufficient integrity for there, and you may not need the sequential type implementation. I'm not sure if that's if that's what they're wondering.
Okay. Our next question is from Jim Farrell. He says, this presentation addresses correlations and measurement errors. Another related issue involves correlations in plant dynamics process noise. Has the methodology presented here been addressed for applications involving that other issue?
Yeah, thank you very much, Jim, for that question. I'm sorry if that wasn't clear. This work does apply equally well to correlated measurement and process noise. So it's not just correlated measurement noise and I have to do something else or figure out something else for correlated process noise. It applies to both.
Okay, great. Our next question says, thanks for the interesting presentation. The problem with undefined parameters of Markov noise can be solved using an adaptive approach. In other words, estimating unknown parameters when solving the problem. What is your opinion about the possibility of solving the problem using such a statement?
Yeah, thank you. That's a really good question. I think the real difficulty with the approaches that involve, so maybe I'll just try to say what I think is the tricky part here when you don't know what the structure is. So if I have no idea what the structure is, I don't quite know how many states are necessary to model the noise. And I think that's the really difficult part, to try to adapt the approach that was taken here and built on from reference 4 to that case where maybe I don't necessarily know what the structure is. I'm not saying that it's not possible, but I'm a little bit skeptical maybe that much headway can be made using that approach.
Okay, thank you. David asks, says, thanks for this brilliant work and presentation. As for you and your team, is there a research subject now connected to your work related to the characterization of TAU, time correlations in errors, and not only the characterization of error bounds, particularly in the urban environment? How did you fix TAU min and TAU max in your illustration for ARAIM? And would it be environment dependent?
Yeah, that's an excellent question. And this is where I've always struggled when I was playing around with this problem in the past is, where do these bounds come from? You know, they've got to be informed from data or something. You know, how do you do that? So to answer your first question as far as ARAIN, I think those we used a little bit of guidance from, you know, previous publications on what it looked like a time constant was, but predominantly those were just kind of taken out of air. We did not collect any extensive data and try to, you know, figure out what to put for tau min and tau max. So what I want to point you to, if you can still see the slides, there was an interesting paper by Sandeep Jada and Matthew Yorger, reference 9 here, that did look at, you know, trying to develop a data, you know, how do I use data to derive bounds on tau min and tau max? And in the general case, I think you're absolutely right. I think it would be environment dependent, especially if you're in an urban environment, or you could even think about, even in open sky, errors being dependent on satellite elevation. So, you know, how I overbound, you know, do I overbound just the entire thing over all elevation angles, or do I bin it? You know, what are the details of that process? So there's a lot of work that still needs to be done in that area.
All right. Mohammed asks, thank you. How to estimate sigma min and sigma max from simulations or previous data? Do you have any real examples?
Yeah, so sigma, yeah, so in the paper, this is something I didn't really touch on too much in the presentation here, but there's also the question of, like, you know, the variance of the Gauss Markov process is probably something I don't exactly know either. Sigma bounding tends to be a little bit easier than trying to find bounds on tau min and tau max, because you can in fact take quite a bit of data to get a bound on sigma, you know, get sigma min and sigma max. There is quite a bit of work on sigma overbounding, and I'm inclined to say that even some of the CDF overbounding theory might apply to that as well. But I may need to think about that one a little bit more. But I definitely feel comfortable saying that getting bounds on sigma is going to be much easier. And I think there's existing literature to guide you on that compared to getting bounds on tau.
Okay. Well, thank you. I think that's the end of our questions. Do you have, Steve, an email address or a way that someone may contact you?
Yeah, thanks, Rick. Yes, I do.
Perfect. So if you have any additional questions, feel free to contact Dr. Langle. We certainly appreciate your time and the efforts of you and your co-authors in presenting this work for us. A recording of today's presentation will be available on our website. We'll have that up within 24 hours, possibly later today. And we'll also have a copy of the slide deck as well. So again, Dr. Langle, thank you for your time, and we wish everyone a good day.
Thank you, Rick, and thanks everyone for listening. Bye-bye.